Hi, my name is Vincent, and today I'm going to talk about the third topic of the lab, which is black hole. And in the introduction of this lab, I'm going to give the purpose and then the models and fundamental principles and how the code and the principles are presented. And then later I will answer some further questions. In the purpose of this lab, I'm going to divide into like two parts. First is from the motion of the star analysis. I'm going to determine the mass of the black hole. And the second part is from the mass of the black hole that I got from the first part. I'm going to determine the initial velocity of the spaceship to get close enough to the black hole without crashing. And this is a trial error, so I'm going to try a lot of errors and to find the initial velocity. And first, I'm going to talk about the main principles, which is the Newton's second law and the gravitational force that acts on these objects. And the gravitational force illustrates how mass and distance affect gravitational attraction, indicating that the larger masses attract each other more strongly, while increasing distance weakens the force between them. And the Newton's second law indicates that the rate of a change of a particle's momentum p is given by the force acting on the particle over delta t. And in the first part, first we are given the initial condition, that is the gravitational constant, the mass of the star, and the time interval, which is 1 day, like 24 hours. And later we are given the functions to calculate and update the star velocity. And in this one, I've changed my C into my Gmail. And in the later of the code, we are given the velocity components from the update formula, and then I'm going to change to find the momentum vectors. Like the initial vector will become the star mass multiplied by the initial vector, and the final momentum will equals to the star mass multiplied by the final velocity. And then I'm going to find the delta V and delta P, and then from that we're going to find the net force, and then we are going to find the parallel dP over dt, and then it is like to find the F net, like the force total net of parallel direction, and from then we're going to find the total force net of the perpendicular direction. And using the equations of the gravitational one, I'm going to find the mass of the black hole, which is equal to dP over dt multiplied by the distance square, and then all over it divide by the gravitational constant multiplied by the mass of the star. Like we'll be updated like a lot of mass of the star, mass of the black hole based on like its orbit. And then to calculate the overall mass, I'm going to calculate the average mass, which is equal to roughly about like 1.69515 multiplied by 10 over 34. And we can also see that the F net total is equal to 9.3 multiplied by 10 over 28, and the F net parallel is equal to 1.533 multiplied by 10 28, and then the F net perpendicular is to 9.24 multiplied by 10 over 28. So in the second part of the closed grip model, I'm going to give the initial planet velocity, which these are first order constants. They are the gravitational constants and the planet mass and the ship mass. And then I'm going to change my black hole mass that I find it in the first part. And then I'm going to try and error a lot of time to find the ship speed in x direction and y direction to find the velocity of the ship and the ship speed, and then to make sure that it didn't crash. And how in the later part, this is the most important part. First, I'm going to find the total force net on the planet, which is divided by 2 total force net, which is the black hole on the planet and the ship on the planet. And then I'm going to find the distance, like using the difference in positions and then the direction of that distance. And then from that, I'm going to find the net force of the black hole on the planet, and then the net force of the ship on the planet. And then I'm going to add it together to find the net force on the planet in total. And then in the second part, I'm going to do similar. It's like the same, but this time I want to find the total force of the black hole on the ship and the total force of the planet on the ship to find the total force together, like all in total on the ship. And then I'm going to use the updated velocity equations that we all have studied, which is the final velocity equals to the initial velocity plus the total F force divided by mass multiplied by time. And then the difference in position will equals to delta t multiplied by the final velocity, because it's a non-constant force. So this is how I've got my my trials and errors done. Like when the star is from a long you can see on the left, it's like a smaller scale of this picture. So this ensures that the ship didn't crash into anything until it gets closer to the black hole. And that is when the ship is now 1.8.048 multiplied by 10 over 11 away from the event horizon of the black hole. So the errors that may possibly happen leads to the differentiation in models is maybe the rounding errors or the rounding of data that may lead to numerical errors. And we assume that there are no other force outside acting on the system, aside from all the forces that we have discussed. And then we could get the spaceship closer to the black hole with more precise calculations and vectors. And here is, I'm going to answer some further questions, is how is the net force and its parallel component different from the rate of change in momentums and its components? So to calculate the net force, we should know the individual factor exerting on the system, but the rate of change allows us to know like the change in only the motion. And like this is when like for the ship to like complete one orbit, and I have done like so many trials and errors, and then I've concluded that if the ship of the speed is around like negative 0.25 times 10 over 7, and then the ship speed in y direction is about 11 multiplied by 10 over 6, it will complete like a like full orbit around the black hole. So thank you a lot for your listening and your time.